This talk is about constant length labeling schemes for deterministic radio broadcast. I am Faith Ellen from the University of Toronto. I will be talking primarily about work I did over the past couple of years with Avery Miller, Barun Gorain, Andre Pelk, and Seth Gilbert. The model of computation is a fixed topology network with n nodes. It is synchronous with time divided into slots. In each time slot, a node can decide whether or not to transmit. If it does not transmit, but exactly one of its neighbors does transmit, it receives the message that neighbor sent. If two or more neighbors of the node transmit in the same slot, then there is a collision and the node does not receive anything. In the figure, there are two nodes that are transmitting, this one and this one. The two nodes in orange receive the message from the top transmitting node. The other two white nodes receive nothing. This left one because two of its neighbors are transmitting, and the right one because its only neighbor is not transmitting. In the radio broadcast problem, the network contains one node called the source that knows the message M, and the goal is to ensure that all nodes eventually know M. The same algorithm is used by each node to determine when it should transmit. This can depend on the history of the node. For example, if the node has not yet received M, it should not transmit. Deterministic radio broadcast means the algorithm used by nodes to determine when to transmit is deterministic. If the nodes have no identifiers, there are networks, for example, a 4-cycle, in which deterministic radio broadcast is impossible. When the source transmits the message M, both neighbors of the source receive the message. In each subsequent slot, they both transmit or neither transmits, since they are performing the same algorithm and they have the same history. In either case, the remaining node does not receive the message. If each node has a distinct log n bit identifier or label, then a round-robin schedule completes with an O of d n slots, where d is the source eccentricity. This is the maximum distance from the source to any node. In the network illustrated here, d is equal to 2. A deterministic radio broadcast algorithm consists of two parts: a labeling scheme, which assigns a label to each node of a network, and a transmission protocol, which enables each node to decide, based on its label and its history so far, whether to transmit, and if so, what to transmit. The first interesting deterministic radio broadcast algorithm was published by Klamtak and Weinstein in 1991. They gave an O of log squared n algorithm for networks with source eccentricity 2, and then used this algorithm one level at a time to get an O of d log squared n algorithm for networks with source eccentricity d. Their algorithm assumes nodes have distinct identifiers. Over the next 16 years, there was a series of increasingly faster deterministic radio broadcast algorithms, culminating in an algorithm by Kowalski and Pelk, which uses d plus O of log squared n slots for networks with source eccentricity d. Their algorithm is as fast as possible, matching a lower bound by Alon, Barnoy, Lineal, and Peleg from 1991, which says there are networks with source eccentricity d for which omega of d plus log squared n slots are necessary. A year ago, Gorain, Miller, Pelk, and I showed that 2-bit labels are sufficient to perform deterministic radio broadcast for any network. Like the algorithms on the previous slide, the label of each node is carefully chosen based on knowledge of the entire network. The broadcast always completes within 2n-3 slots, and there are networks for which 2n-3 slots are used. This year, Gilbert and I gave a deterministic radio broadcast algorithm using 4 bits for each label, which completes within O of square root of nd slots, which is faster when d is the O of n. Then we defined the class of continuous broadcast algorithms, which includes both of these algorithms. And we proved that any algorithm in this class requires omega of square root of nd slots for some network. In other words, our algorithm is optimal in this class. We also came up with a different algorithm that is not in this class. It uses only 3-bit labels and completes an O of d log n plus log squared n slots. This is better than any continuous broadcast algorithm if the source eccentricity d is little o of n divided by log squared n. The problem with this algorithm is that it is non-constructive. We rely on the probabilistic method to show that, for any network, there's a good choice for the 3-bit labels on its nodes. Finally, we give another algorithm with 3-bit labels that takes slightly longer, but there is a deterministic algorithm for constructing the label of each node in a network. I'll begin by presenting the algorithm from 2019, but before that, I need a couple of definitions. A set of nodes X is said to be a dominating set for a set of nodes Y if every node in Y has a neighbor that is an X. For example, in the first network and in the second network, the set of brown nodes is a dominating set for the set of orange nodes, because every orange node has a brown node as a neighbor. However, this is not true in the third network, since the middle orange node has no brown neighbor. X is a minimal dominating set for Y if it is a dominating set for Y, and no proper subset of X is a dominating set for Y. For example, in the second network, the set of brown nodes is a minimal dominating set for the set of orange nodes. But in the first network, the set of brown nodes is not a minimal dominating set for the set of orange nodes, since you can remove this bottom brown node from the set, and we still have a dominating set for Y. Why are minimal dominating sets useful for radio broadcast? They have the following nice property. Suppose that X is a minimal dominating set for Y, and all nodes in X know the source message. Now consider a slot in which only the nodes in X transmit, and they all transmit the source message. Then for each node U in X, there's some node V in Y that receives the source message from U. Node V is called a private neighbor of U. For example, the top two orange nodes are private neighbors of the top brown node, and the bottom orange node is a private neighbor of the bottom brown node. Now let's see why it is true that every node in the set X has a private neighbor in the set Y. For contradiction, suppose that some node U in X doesn't have a private neighbor in Y. Then X minus U is still a dominating set for Y. This contradicts the assumption that X is a minimal dominating set for Y. In the dominating set mechanism, each node has a label consisting of 2 bits, which are called the join bit and the stay bit. Slots are grouped into rounds with 2 slots each, a dominator slot and a feedback slot. At the beginning of each round R, 3 sets of nodes are defined. Informed is the set of nodes that know the source message. Frontier is the set of nodes that don't know the source message, but have at least one neighbor that does. Finally, DOM is a subset of the informed nodes that is a minimal dominating set for the frontier nodes. In the dominator slot, each node in DOM transmits the source message. Each node in the frontier that receives the source message in this slot is said to be newly informed. It joins the minimal dominating set for the next round if and only if its join bit is 1. Each node in DOM has at least one newly informed private neighbor in the frontier. One such node is chosen to be its designated feedback node. If the stay bit of a node in the frontier is 1, then it transmits 1 in the following feedback slot. A node in DOM stays in the dominating set for the next round if and only if it receives a 1 from its designated feedback node in the feedback slot. The join and stay bits can be constructed by simulating the algorithm one round at a time and using a greedy algorithm to construct a minimal dominating set for the round. For example, in the first round, the minimal dominating set consists of the source, and the frontier consists of its neighbors. Each node in the frontier receives the message. They all have stay bit 0, so they don't transmit in the feedback slot, and the source leaves the dominating set. The top 2 orange nodes have join bit 1, so they join the dominating set. In the second round, the 2 brown nodes are in the dominating set, and they transmit the source message in the dominator slot. The 3 orange nodes constitute the frontier, and 2 of these nodes receive the source message, the top one and the bottom one. The top orange node has stay bit 1, so it transmits in the feedback slot. It is the designated feedback node for the top brown node. So the top brown node stays in the minimal dominating set. The top orange node also has join bit 1, so it joins the minimal dominating set. The designated feedback node for the other brown node is the bottom orange node, which has stay bit 0 and join bit 0. Hence, neither of these two nodes are in the new minimal dominating set for round 3. In the third round, the two brown nodes at the top are the dominating set, and they transmit the source message in the dominator slot. The two orange nodes in the frontier both receive the source message in the dominator slot, and both have their stay and join bits equal to 0 since the broadcast is complete. The level dominating set mechanism is a modification of the dominating set mechanism. It makes use of the level of each node, which is its distance from the source. For example, in this network, the nodes in the brown circle are in level 1. The nodes in the orange circle are in level 2, and the node in the yellow circle is in level 3. It follows from breadth-first search that the neighbors of a node in level L are in levels L-1, L, or L+1. First, let's consider the special case when the source eccentricity is 2. In round 1, the dominating set consists of the source, and the frontier consists of the nodes in level 1. In subsequent rounds, the frontier is contained in level 2, and we choose the dominating set to be contained in level 1. We can show that the dominating set mechanism completes in 1 plus the minimum of the size of level 1, and the square root of 2 times the size of level 2, which is O of square root of n. In the general case, in order to keep the levels separate, there are 2 additional bits in the label of each node, which are used to record its level mod 3. When a node transmits the source message M, it also sends its level mod 3. This enables a node that receives the message to determine whether it comes from the same level as itself, one earlier level, or one later level. To make the algorithm behave like the source eccentricity 2 case, a node in the frontier ignores a message containing M unless it comes from the level immediately before it. The labeling algorithm also ensures that the subset of DOM at some level L-1 is a minimal dominating set for the part of the frontier at the next level. To prevent interference between different levels, only nodes and levels that are multiples of 3 apart can transmit in the same slot. For example, nodes at levels 0, 3, and 6 can transmit the source message M in the same dominator slot if they are in the minimal dominating set for that round. And nodes at levels 1, 4, and 7 can transmit in the feedback slot if they are designated feedback nodes for that round. Since there are d pairs of levels, and it takes O of square root of n rounds for one level, it's easy to see that O of square root of n rounds suffice. With a more careful analysis, we're able to show that an O of square root of nd round upper bound. Since each round consists of 2 slots, this is O of square root of nd slots. Now, I'll informally define the class of continuous broadcast algorithms. Suppose all nodes in level L first receive the source message M in the same slot, drawn in blue in this diagram. The slots in brown are those in which there are nodes in level L that transmit M. In a continuous broadcast algorithm, a node V in level M could transmit M in all of the brown slots, or in some prefix of these slots, but cannot skip one of these slots and then transmit M later. Formally, a broadcast algorithm is continuous if it satisfies this technical property. For every network and for every level of that network, if all nodes in level L first receive the source message M in the same slot S, then for every node V in level L, if V transmits M in a later slot S double prime, and there is a slot S prime between S and S double prime, in which some node in level L transmits M, then V also transmits M in slot S prime. Both the dominating set mechanism and the level dominating set mechanism that I just described are examples of continuous broadcast algorithms. This is the weakest generalization of these 2 algorithms that we could come up with and prove the following lower bound. For any continuous broadcast algorithm, there's a network with n nodes and source eccentricity d that requires omega of square root of nd slots. This is a picture of that network when d is equal to 6 and n is equal to 30. To get faster algorithms, we start with the dominating set mechanism, but add 1 more bit and 1 more slot. The new bit is called the go bit, and the new slot is called the propagation slot. The propagation mechanism behaves the same as the dominating set mechanism in the dominator slot. Namely, each node in the dominating set transmits the source message. The only difference in the feedback slot is that each designated feedback node transmits its go bit as well as its stay bit. A node in the dominating set also transmits the source message in the propagation slot if it received a go bit with value 1 from its designated feedback node in the feedback slot. Otherwise, it does not transmit during the propagation slot. The join and stay bits are constructed as in the dominating set mechanism by simulating the algorithm, one round at a time. However, the go bits are constructed probabilistically prior to running the algorithm. For each round R, a random value p between 1 and log n is chosen, and the go bit of each designated feedback node in round R is chosen to be 1 with probability 1 over 2 to the p. If p is 1, then the go bit of each designated feedback node is equally likely to be 0 or 1, whereas if p is log n, then its go bit is 1 with probability only 1 over n. If node v is in the frontier, then v receives the source message m in the propagation slot with probability O of 1 over log n. This part of our algorithm is related to the randomized decay algorithm for those of you who are familiar with it, and it has similar performance. Now let me prove this lemma. Since there are log n choices for p, the probability that p lies between d and 2d is at least 1 over log n, where d is the number of neighbors of v in the dominating set. An extra factor of 2 arises to get rid of the ceiling. The probability that a specific neighbor of v in the dominating set transmits in the propagation slot is 1 over 2 to the p. The probability that none of the other d-1 neighbors of v in the dominating set transmits in the propagation slot is 1 minus this amount to the power d-1. So the probability that exactly one of v's d neighbors in the dominating set transmits in the propagation slot is d times this amount. If p lies between d and 2d, then the probability that exactly one of these neighbors transmits in the propagation slot is at least 1 over 15. Hence, the probability that both these events occur is the product of these two probabilities, which is 1 over 30 log n. Then, by a Chernoff bound, there's a high probability that any particular node in level L knows the source message with an O of L log n plus log squared n rounds. Finally, by a union bound with high probability, every node knows the source message with an O of d log n plus log squared n rounds. Hence, by the probabilistic method, for any network, there exists a choice for all the go bits so that the propagation mechanism completes with an O of d log n plus log squared n rounds. Since each round consists of 3 slots, this is also an upper bound in the number of slots. Thus, our algorithm, which uses only 3-bit labels, runs almost as fast as the best deterministic radio broadcast algorithm, which uses large labels. Next, I want to discuss Klamtak and Weinstein's algorithm for graphs with source eccentricity 2. It relies on the following lemma about connected bipartite graphs, where x is one part and y is the other part. The lemma says that there is an efficient algorithm to compute a subset x prime of x and subprime y prime of y, such that y prime is reasonably large, and each node in y prime has exactly one neighbor in x prime. So this node has that neighbor, and this node has that neighbor. The first part of this lemma is similar to the proof of the lemma I proved 4 slides ago. Let yp denote the set of nodes in part y of the bipartite graph that have between 2 to the p minus 1 and 2 to the p neighbors. If each node in x transmits with probability 1 over 2 to the p, then each node in yp has probability at least 1 over 15 of receiving the message. Suppose p is chosen so that yp is the largest of these sets. By the pigeonhole principle, the number of elements it contains is at least 1 over the number of different choices for p. Then the expected number of nodes in yp, and hence y, that receive the message is at least mu, where mu is this quantity. Next, we randomized using the technique of conditional expectation. We initialize x prime and x double prime to be empty and consider the nodes u and x one by one. We consider 2 experiments, one where u transmits and one where u doesn't transmit. In both experiments, all nodes in x prime transmit, no nodes in X double prime transmit, and each other node in X transmits with probability 1 over 2 to the p. In at least one of these two experiments, the expected number of nodes in Y that receives the message is at least mu. If the expected number of nodes in Y that receives the message is larger in the first experiment than in the second, add U to X prime, otherwise add U to X double prime. This maintains the invariant that the expected number of nodes in Y that receive a message is at least mu if all the nodes in X prime transmit, no nodes in X double prime transmit, and each other node in X transmits with probability 1 over 2 to the p. After all nodes in X are either in X prime or X double prime, let Y prime be the set of nodes in Y that receive a message when all nodes in X prime transmit and no nodes in X double prime transmit. These are the nodes in Y that have exactly one neighbor in X prime. The invariant ensures that the size of Y prime is at least mu. Now we'll present Klamtak and Weinstein's algorithm for networks with source eccentricity 2. In round 1, the source transmits the source message M, and all nodes at level 1 become informed. In round 2, we apply the lemma where X is the set of nodes at level 1 and Y is the set of nodes at level 2. The nodes in X prime transmit M in round 2, and the nodes in Y prime are informed. In round 3, we apply the lemma where X is the set of nodes in level 1 and Y is the set of uninformed nodes at level 2. The nodes in the new set X prime transmit M, and the nodes in the new set Y prime become informed. It can be proved that within 15 log squared n rounds, all nodes in level 2 are informed. To construct the Go bits deterministically, we use the same lemma, but apply it to different sets X and Y. Specifically, in each round R, Y is the set of all uninformed nodes in the smallest level L that contains uninformed nodes, and X is the subset of the nodes in the minimal dominating set for round R that occur in level L-1. We are able to prove that once every node in some level knows the source message, every node in the next level knows the source message within 15 log squared n more rounds. Since each round consists of 3 slots, it follows that the propagation mechanism completes within O of d log squared n slots, where d is the source eccentricity. This is just slightly slower than the O of d log n plus log squared n slots when the Go bits are determined using the probabilistic method. We've shown that for any network, there exists a choice for the Go bits so that every node knows the source message within O of d log n plus log squared n slots. And there's a deterministic method to construct the Go bits so that every node knows the source message within O of d log squared n slots. An open question that remains is the existence of a deterministic radio broadcast algorithm using a constant number of bits for the label of each node, which completes in O of d plus log squared n slots, matching the lower bound for arbitrarily large labels. For some families of networks, it's possible to perform deterministic radio broadcast using smaller labels. For example, in trees, labels are not needed. Each process simply transmits the source message in the slot after it first receives it. The structure of the network ensures that there are no conflicts. In networks with source eccentricity 1, the source directly transmits the message M to all other nodes, so deterministic radio broadcast can also be performed without labels. In networks with source eccentricity 2, a slight variant of the level dominating set mechanism works using 1-bit labels. Nodes in level 2 never transmit, so their join bits are all 0. The source successfully transmits to all its neighbors in the first round, so it doesn't stay in the dominating set. Hence, the stay bits of all nodes in level 1 are 0. If the source node transmits M0 and nodes in level 1 transmit M1, a node learns its level when it first receives M. Thus, only 1-bit bit labels are needed. Notice that the label has a different meaning for nodes in level 1 and nodes in level 2. For nodes in level 1, its label is its join bit, and for nodes in level 2, its label is its stay bit. Earlier this year, another family of networks was defined for which deterministic radio broadcast can be performed using 1-bit labels. A network is said to be level separable if for every level, except the last level, the level consisting of the source, the nodes in that level can be partitioned in two parts, here colored red and brown, so that every node in the next level has exactly one red neighbor or exactly one brown neighbor. In this example of a level separable network, the top 3 orange nodes each have one red neighbor, and the bottom orange node has one brown neighbor. The second orange node also has one brown neighbor, but that's okay. In the first slot, the source transmits. In the next slot, the red node in level 1 transmits. Well, all the red nodes in level 1 transmit. And in the following slot, the brown nodes in level 1 transmit. This ensures that all nodes in level 2 are informed. If the source eccentricity is greater than 2, then in the next round, which consists of 2 slots, the nodes in level 2 transmit one part at a time. This continues one level per round until the nodes in level D are informed. A two-dimensional grid is an example of a level separable network. In the diagram, I've circled the nodes at level 3, assuming that the black node is the source. The top 3 nodes in level 4 each have one red neighbor and one brown neighbor in level 3. And the bottom node in level 4 has one brown neighbor and no red neighbors in level 3. Since 2-bit labels are sufficient for deterministic radio broadcast in any network, and deterministic radio broadcast is impossible without labels in a cycle of length 4, a question that remains is whether 1-bit labels are sufficient for deterministic radio broadcast in any network. If not, it would be nice to characterize the family of networks for which 1-bit labels suffice. An extension of deterministic radio broadcast is acknowledged broadcast, where the source receives an acknowledgement message in some slot after all nodes receive M. This is useful when the source wants to continue with another algorithm without interference from the broadcast. Acknowledged broadcast can be accomplished using one additional bit per label. To label the nodes in the network, first simulate the deterministic radio broadcast algorithm to get the join and stay bits. Then choose a node Z that is informed last and set its extra bit to 1. Note that its join and stay bits are both 0. Next, choose some shortest path between the source and Z, in which the nodes in between the source and Z all have join bit 1. This is possible since the nodes with join bit 1 are the only nodes besides the source that transmit M. The extra bits of the nodes on this path are set to 1. The extra bits of all nodes not on this path are set to 0. The first part of the transmission protocol is the same as the dominating set mechanism or the level dominating mechanism. When the node Z first receives the source message, it transmits acknowledgement in the next slot. It is the only node with join bit 0 and extra bit 1. When a node with join bit 1 and extra bit 1 first receives an acknowledgement, it forwards that acknowledgement in the next slot. The acknowledgement travels along the chosen path, one node per slot without conflicts until it reaches the source. Another extension of deterministic radio broadcast considers what happens if the nodes of the network are labeled before the source is chosen. In this case, a variant of acknowledged broadcast can be used. The idea is that the labeling is done using a fixed node with smallest eccentricity as a surrogate source. During the broadcast algorithm, the surrogate source broadcasts a request for a message. Instead of the fixed node Z initiating the acknowledgement, the actual source acknowledges with the source message M. Finally, the surrogate source broadcasts M on behalf of the actual source. Because the actual source is not chosen before the nodes of the network are labeled, we need a more complicated version of acknowledged broadcast, which I'll now present. The idea of this version of broadcast is that the acknowledgement that Z transmits when it receives M will travel back to the source along the reverse of the path that M took from the source to Z. In particular, the unique node Z1 that informs Z will transmit an acknowledgement the slot after it receives the acknowledgement from Z. Likewise, the unique node Z2 that informed Z1 will transmit an acknowledgement the slot after it receives the acknowledgement from Z1. This continues until the source finally receives an acknowledgement. To facilitate this, the source sends a counter C, which initially has value 1 along with M. We'll call this counter C. When a node V first receives M, it stores the value of C. Node V also sets a local counter to C, which it increments each round. When V transmits M, it sends the value of its local counter along with M and keeps track of the values of its local counter that it has sent. Let's see what happens in this network. In round 1, the source sends M1 to both its neighbors. When they receive the transmission, they store the value 1 and initialize their local counters to value 1. In round 2, both neighbors of the source are the dominating set. They transmit the message M2, and they record that they've sent a message with counter value 2. The little square beneath each node is the list of counter values that they've sent in messages. In round 3, the 2 brown nodes are the dominating set. They transmit the message M3, and they record that they've sent a message with counter value 3. The 3 orange nodes receive this message and store 3 as the counter value when they first received M. In round 4, Z transmits an acknowledgement together with 3, the counter value when it first received M. All of Z's neighbors receive this message, but only one of them, Z1, had transmitted a message with counter value 3. In round 5, Z1 transmits an acknowledgement together with 2, the counter value when it first received M. All of Z1's neighbors receive this message, but only one of them, Z2, had transmitted a message with counter value 2. Finally, in round 6, Z2 transmits an acknowledgement together with 1, the counter value when it first received M. All of Z2's neighbors receive this message, including the source, completing the acknowledged broadcast. An open question that remains is whether an extra bit is needed for acknowledged broadcast or for broadcast from an arbitrary source. Finally, suppose that nodes can detect conflicts. This means that if 2 or more neighbors of a node transmit in the same slot, then the node receives a special conflict message instead of receiving nothing. Can broadcast, acknowledged broadcast, or broadcast from an arbitrary source be performed using smaller labels or fewer slots in this model? Thank you very much for listening to this talk.